Yeah, thank you for the invitation. It's a great pleasure for me to be here. In actual fact, this talk is a kind of continuation to your lecture that you just gave. There will be certain references to it. So, okay, now first of all, I will give you a review of work that I did with Dragi Karevsky from Nancy and with Vladimir Popkov, who is working with me in Bonn. And well, here you see the outline. The first part will be very general, just to give you the main ideas. And then I will talk a little bit about how to do this matrix product that you just heard about, how you do it for quantum systems. And then I will give you some results that we got in recent years. So, well, first of all, what are non-equilibrium steady states? Well, basically, I think most of you will know it, but really what we are looking at are at open systems. So you have some system of particles or atoms of something, and now we assume that it's open to some environment at one end and open at another environment to another end, where you have some conserved quantity inside, which I just indexed by a density rho. It can be a mass density, a particle density, or any energy density, any density you can think of. And here we pump in this conserved quantity, and here we take it out. So we generate a current. That's the basic setting of what we have in mind. So again, to summarize, here in the bulk, we have some conservation laws, mass, energy, whatever. Then we have open boundaries with reservoirs, two different reservoirs, 1 and 2, which then will generate some gradients. So we assume that the densities of these conserved quantities are different at the two boundaries. And as a result, there will be currents. There will be density profiles, so the density of these conserved quantities will not be constant anymore along the chain, and of course there will be correlations. Now, and what these currents indicate is that we are not in thermal equilibrium. So that's the most general terms what I have in mind. Now, if we are close to equilibrium, that means if these differences of these boundary quantities, this balance, are very small, then basically we can do kind of linear response theory. We will have some local thermal equilibrium in the bulk, which is basically the same as the global equilibrium because this deviation is very small. So we can use the rules of thermodynamics, and then linear response theory will give us for diffusion, if the conserved quantity is mass, will be Fick's law, or if the energy is conserved, we will get Fourier law, and if we have electrical charge that are conserved, we will get Ohm's law, and so on. And the currents, they will be proportional to the gradients of these quantities, in some sense, with some matrix, if they have several, divided by the system length, and this is what's normally called normal transport. Now, if we are far from equilibrium, meaning these imbalances are not small anymore, well, then we cannot simply apply this theory because it's a perturbative theory. We cannot just rely on it. What happens instead that we have our bulk dynamics, and they will have some kind of interplay with this boundary pumping, which is not so obvious anymore how it goes. So it's theoretically quite challenging because since we're not in equilibrium anymore, we don't have a Boltzmann weight to describe our ensemble. Instead, we have a non-equilibrium steady state, stationary state, which is often called abbreviated NES. And since the response will be in general be nonlinear, well, we cannot apply these theories, but we have to rely on either numerical solutions or on heuristic theories. That's the standard setting. Okay, now this is very general, but in the title you saw spin chains. That indicates that I will actually talk about one-dimensional systems, quasi-one-dimensional more precisely, because they're actually quite special when it comes to non-equilibrium phenomena. For instance, it's known that you have phase transitions which can be induced just by these boundary parameters, by this boundary what you put in the boundaries. You can have phase separation, you can have spontaneous symmetry breaking, which are phenomena which are not spectacular, but in one-dimensional equilibrium they cannot occur. But far from equilibrium they can occur. So this is really special here, and one wants to understand why. And then, and this will be more what I'm going to talk about, you can have anomalous transport phenomena. You can have ballistic and other superdiffusive transport, and I've seen that next week there will be a talk about this by David Mukamel, and I will also talk about this in quantum context. You can have subdiffusion, you can have non-Gaussian fluctuations, and many more. So that's one of the reasons why we're particularly interested in one-dimensional systems, but also because we have many more methods to actually treat them. Just to give you some examples of classical one-dimensional systems where the dynamics is noisy due to thermal noise, I will have in mind diffusive systems, but there are others, but I will only think of diffusive systems that you have also just heard about in the lecture of Bernard. So you think of mass transport. For instance, this can happen as molecular diffusion in carbon nanotubes or in zeolites. Here's just a sketch of such a carbon nanotube where you have different kinds of particles inside. Or you can have colloidal particles in narrow channels. Now this is a real picture from the group of Bechinger in Stuttgart. So they etch a little channel in glass, and then they could put colloidal particles, which then can diffuse in this channel. Or also you can go to complex systems outside physics. For instance, if you think of molecular motors in biological cells, they're also quasi-one-dimensional. Molecular motor is a microscopic object that performs some function in a cell, such as the production of a protein. And then what it does, it moves along some template, which can be a DNA or an RNA or a microtubulus. And while they move, they perform their task. And you can have many of them. So they move, and again, this is a real picture. They can move along, in this case, a messenger RNA, produce proteins, and as they move, well, they have a random motion, which is thermally activated. So you also get some kind of diffusive dynamics here. Now, when I think of quantum systems, I have, again, there are many settings where this can occur. Again, I'm thinking of quasi-one-dimensional systems where the conserved quantities are typically energy and magnetization or spin. Now, the way where this happens are spin chain materials, for instance, which are, of course, three-dimensional objects. However, here you can see this is a kind of two-dimensional presentation of a certain chemical compound, where you have kind of chains which have little interaction in their perpendicular direction with other chains. That's therefore these chains here, they're quasi-one-dimensional in here. And you can measure, now the picture is somehow bad, you can measure all kinds of quantities, which anyway in this case are not so important here, just to illustrate that such materials exist and that people can make experiments on them. Or what has become a really big thing in the last 5 or 10 years are arrays of cold atoms in the optical lattice. So basically, you can create artificially with lasers, you can create a one-dimensional lattice, and you can take ultra-cold atoms, put them inside, and then you can let them interact in one direction only. So here again, these are pictures taken from a website, which I guess one can't read now, but you can have the source if you wish. So here you have, well, these are kind of two parallel chains, and these blue dots, they are the atoms that have been investigated. Here you can see that these atoms have spins. It's just a kind of sketch of what you see here to illustrate what is there. Okay, so now this is what one can study. Now, if you think of classical systems, we have pretty good, and just for illustration, just take one conserved quantity, like just one mass, which is what we just heard about in Bernard's lecture. We know that we have very good theories to describe this phenomena. So basically what you have, that locally you still have a local equilibrium, as if it was very close globally close to equilibrium, but even when it's far from equilibrium globally, locally we'll still have an equilibrium situation at some density rho of x. And then the stationary current that flows and the density profile, they are determined by the diffusion coefficient, which can be a function of the density, and these boundary densities via the stationary diffusion equation, which we also have just seen on the blackboard. So the derivative of the current has to be 0 because of stationarity and the conservation law, and then the current itself is minus the diffusion coefficient times the gradient of the density. Okay, so this gives you the profile and the current by putting the boundaries plus and minus, rho plus and rho minus. But one can go beyond, one can study fluctuations, and then the theory of fluctuating dynamics, which was basically elaborated by Spohn already in 1983, tells you that you generally expect long-range stationary correlations, which comes from the fluctuations and the fact that you're really far from equilibrium. Now here an example that you also have just seen before, the one symmetric simple exclusion process. So you have a lattice where particles jump to the right and to the left. In general, these rates can be different, but in the symmetric case, they are the same. And they are equal to the diffusion coefficient, which for this particular model does not depend on the density. It's just a constant, just equal to these hopping rates. And here are your reservoirs. So here you put in particles with a fixed density rho minus, and you take them out, or also put in, depending. You just exchange particles here, and if these two densities are not the same, they're different, you will introduce this gradient, and the current that will come will be equal to minus this density difference divided by L, so this will be normal transport. The density profile is going to be a linear function. Since d is a constant, the solution of this equation is just a linear function, interpolating between these two boundary densities. And then the correlation function have been computed by Spohn. Well, they are of the form that we also just saw. They have an amplitude 1 over L. They are anticorrelated. And then here is the actual functional form. It's the density difference to the boundaries. It's just the product. It factorizes in these two densities. So for instance, if you have a maximal driving, meaning boundary density 1 here and 0 there, 1 because it's exclusion, you can have at most 1, this will be, the function will be 1x times 1 minus x for this correlation function, times 1 over L. Okay, now this is classical. What do we expect for quantum systems? Well, the unfortunate fact is that quantum systems are actually quite poorly understood. We don't have such nice general theories that allows us to make these and many more predictions. So what we have to do is we have to study individual systems and try to get some insight, some information, which we can then at some point in the future use, perhaps, to make a more general theory. That's basically where we are now. Now, so we want to talk about open quantum systems. So first of all, what is an open quantum system? How do I describe it? Let me go back to just normal quantum mechanics, just as a reminder. In quantum mechanics, we describe a physical system by a Hamiltonian, H, its eigenvalues and eigenfunctions, and then we have observables. These H and these OIs, they are Hermitian operators. The ENs, the eigenvalues, are the energy of an eigenstate n, and then these wave functions, they are normalized. But they're orthogonal and they're normalized. And these coefficients are just probability to find the system in some eigenstate n. And expectation values are given by the scalar products, which you can also write as a trace over a density matrix. And the density matrix in this setting is just a tensor product of this two quantum mechanics state of a bra state and a cat state. The time evolution of such system is given by the Schrödinger equation. I just set the h bar constant to be equal to 1, and then the Schrödinger equation for the wave function is just the time derivative of the wave function is minus I times the Hamiltonian acting on the wave function. What's this? And this looks strange. Well, anyway, let's hope it doesn't matter. And if you write the time evolution in equivalent form, you think it's stuck somewhere? Okay, it's disappeared.
Oh, okay, fine. Okay.
Yeah, so let's try again.
Because maybe it tries to connect it.
Yeah, that could be, yeah, right. Okay, and equivalently, this is totally equivalent. You can write the time evolution equation for the density matrix, that rho is this, as a commutator of the density matrix with this h. So these are totally equivalent descriptions. Just want to introduce the notion of density matrix because this will be useful. Now, what do we assume by describing quantum system in these terms, which you have learned all in your first year quantum mechanics course? Well, we assume that we are talking about a single system, possibly of many bodies, but we are thinking about one particular physical system. And we also assume that it is completely isolated from its environment. So now, in our case, we're not interested in what just a single system does. We want to study an ensemble of systems. So we want to do statistical properties. We want to do quantum statistics. So again, let's stay in equilibrium. And what we do then is we describe, indeed, the system by density matrix. But the density matrix now is of a specific form. Namely, it's not just this product of wave functions. It's we introduce a quantum Boltzmann weight, which is a matrix, the exponential of minus beta times h. And then we derive a partition function, which is just a trace of this object. And then we obtain the density matrix by taking the Boltzmann weight dividing by the partition function. So this will give you statistical properties, again, of a particular system, which is closed from its environment. So what is this general property of this density matrix? Well, the trace is 1, simply by normalization. Secondly, it's Hermitian. That's because it's exponential of a Hermitian operator. And this is important now, all the diagonal elements, they are strictly positive. And this will be true in this thermal case and also in the pure state that I showed you in the previous slide. And moreover, since we are talking about stationary properties, this will be stationary. And this is simply, again, because here you have the exponential of h. If you take the derivative of this object, you have to take the commutator. And the commutator of h with the exponential is 0. So this will be stationary. Okay. So this is just as a reminder. Now, what do we assume here? Well, again, we assume that the system is completely isolated, and this means it has no interaction whatsoever with its environment. and it didn't have it even in the past, because even if it has no interactions now, if it had interaction in the past, there will still be entanglement, and entanglement has a memory of the past. So we're really thinking of a system that has never been in contact with anything, never ever. So that means this will not be a good approach to study open quantum systems, because by definition they are in contact with some environment, and we want to study the effect of this environment. So we cannot use this kind of equilibrium formalism. We have to do something different. So what do we do? Well, first of all, one way of thinking about it is the following. We take our complete system, let's say the whole universe, and we divide it into an open system, which is one to want to study, and its environment. So this will be this quantum spin chain, or an optical lattice with atoms. And this will be the kind of rest of the universe, where we couple the ends of the chain in two different fashions to this environment. So that means the total Hamiltonian of the whole universe, again, of your completely isolated system, will now split into several parts. There will be Hamiltonian part for the left environment. There will be an interaction between the chain and this left environment. There will be the Hamiltonian of the subsystem, which is here H sub, but later we'll simply call it H for simplicity. Then you have an interaction between the system and the right environment, and you have the Hamiltonian for the right environment. Now, this would still be the complete framework, and you would then say, okay, this is the whole world, but what we want to study is only this part here. So the way how you do it is, well, you look at the reduced density matrix, where you just trace out all the degrees of freedom of your environment. So this rho sub, the density of the matrix of the subsystem, is the trace over the environment of the whole density matrix. Okay. And then the question of interest would be the stationary reduced density matrix of the subsystem, which, however, will not be the exponential of this H sub because of all the interaction and because of the tracing out. So the tracing out can leave trace of entanglement and other phenomena. Okay, so as I say, in the following I will omit this sub. Now, a new problem is that this is something very formal. Of course, you cannot take a trace over the rest of the universe, right? It's obviously nonsensical. You cannot do it. I mean, this is just the idea behind it, but how do you do it? You cannot do it in any explicit form. So what people have studied is the following. Well, since we cannot actually do this for what I just proposed, but we can nevertheless ask ourselves, how can possibly be the evolution of such a reduced density matrix may be, assuming that we want to preserve positivity and normalization, because this is clearly essential, otherwise we cannot compute anything. And this will be essential physical properties. You see, these diagonal elements, they are really probabilities in the classical sense. They have to be positive quantities. And of course, well, we want to study a system where we can normalize it. I mean, you can go beyond, but let's stay with a system where you can actually normalize, where the partition function will be finite. This has been looked at in the 70s and was found that the evolution equation of such a density matrix with these properties, which is, as I say, just a density matrix of the subsystem, this will have this unitary part that we have seen already in an isolated system. So this will be the Hamiltonian of the subsystem. But then the coupling of the environment, this will be described in terms of dissipators. In our case, since we have two environments, there will be two different ones. So we can say that the derivative of this rho will be just some operator, linear operator acting on this density matrix rho, which is not just a commutator, but something else. And now, and here comes really the point, if you want to preserve positivity and normalization, then this dissipative part has to have a very specific structure. Namely, there will be operators, which I will call Lindblad operators, have to act on the density matrix in this particular fashion, in this way and in no other way. Otherwise, you will lose these properties. So it's actually quite constrained. So if you carry out this program and believe in it, what will come out is something of this form. So what you have to do in reality, if you want to look for a non-equilibrium steady state, which is the solution of this equation where L of rho is simply equal to 0, the left-hand side is 0, then, well, what you have to do is you choose your H according to your physical setting. You also choose these boundary dissipators according to what you do in your experiment. You have to kind of guess what operators you have to choose in order to model a situation. Then you solve this equation, this one here, in some way. And then you can compute expectation of physical observables, which will again be just a trace of this observables times the density matrix. So that's the program. Now, again, this is of course very general and cannot be done with great generality, but we can solve and we can treat this one for specific systems. And what I have in mind are now chains of n atoms. So here we have our chain, and each atom has a spin. I was thinking of spin chains. And okay, so the spin is proportional to the magnetic moment. So basically you can say you have magnetic moments that interact. Yeah, this is just proportionality factors. Now, since we are in quantum mechanics, this spin here will not be a classical variable, will not just be a number, but will be a matrix, will be an operator. And since spin is to do with angular momentum, it will be a spin S representation of the algebra of SU2 of this atom I, where SU2 is the kind of quantum version of the rotation group. That means that in the quantum systems, these spin operators, if we have spin 1/2, the lowest non-trivial spin, then this SI will be just a vector of Pauli matrices, which I've given here. So this is just the SU2 representation of SU2. Okay, so now what is our Hamiltonian then? Well, I will look at the Heisenberg spin 1/2 quantum chain, which is where you see that the neighboring spins interact, and we assume the interaction is such that they have a rotation symmetry around the z-axis. So here you have the same exchange coupling constant. Here this one can be different from those because, remember, the spin chain is embedded in the crystal. So you can have different coupling constants in different directions, and we look at the simplest setting here because this has a global conservation law, namely the z component of spin will be conserved. And then we can also allow for boundary fields which come from tracing out the environment. So you may have some remnants of this acting on the boundaries. So now for our computations, these quantities which are of course important in experiment, we can just set for computations equal to, give them certain values. I take j equal to 1/2. This interaction anisotropy, this will be an important parameter, but I parameterize it in this particular fashion, as writing as a cosine or as a cosh, depending on what the q is. Then this energy here, again, is some constant. I set it equal to 1. And just to remind you, this is a matrix of dimension 2 to the power n, because locally, each spin, you can have a spin up or a spin down in that direction. It's 2 states, and then sigma x and sigma y cannot be simultaneously measured. So these are not independent degrees of freedom because of the quantum commutation relations, basically because of Heisenberg's uncertainty relation. So it's a matrix of 2 to the power n, so we somehow then have to treat. Okay, now this is just for illustration. Okay, now how do we choose our boundary? Well, as I say, we have to think of what we can do experimentally, and what we do assume is that we have an apparatus that allows for complete polarization of our magnetic moments in 2 different directions, only at the boundaries, right? This is our coupling. So again, here's our chain, right? And we assume that this magnetic moment here, that we can fix it. And we can fix in 2 different directions, not necessarily related to this quantum fields, right? This is just something internal. So that's the assumption. Now, the way how to do this with the Lindblad operators is, again, to illustrate this situation in this way. So basically, these Lindblad operators are, again, somewhat like a quantum boundary field. However, it will be non-Hermitian, as you can see by these factors I that appear here. And since we fix in 2 different directions, all these coefficients here will be different. Okay, so this will be our setting. Now, again, why is this a good choice? Well, you can imagine that you just forget about the quantum interaction. You just look at what these guys do on your density matrix, omitting the unitary part, and then you realize that the stationary solution of the action of these dissipators is just a factorized density matrix, where at the left boundary you really project on this direction that you have chosen by these weights, and in the bulk you have just anything because there's no interaction. It's just arbitrary. So this really is a way to convince yourself that with these Lindblad operators you really project in these 2 different directions. But now you switch on the quantum interaction, and then of course what happens? Well, you will expect a current, in this case a spin current, you will expect non-trivial magnetization profile, and you will expect non-trivial correlations. And what are they? That's the question. Now, how can we solve this problem? Again, we have a matrix of dimension 2 to the power n, and we have linear operator acting on them. So basically, we have to solve 2 to the power n equations. This is not very difficult if n is small. You can just put it on a computer and solve it. But for large n, this is of course a problem. It grows exponentially in n. So what we do to get an exact solution is the following. We make a matrix product ansatz for this density matrix, which we express in terms of matrices AI and boundary vectors. And this idea was actually introduced by Brosen in 2011. So to make a matrix product ansatz for this density matrix. This is somewhat different to what we have just seen in the lecture. Then, okay, this is just an ansatz. Then you have to say something about the matrices. We have seen how it worked in the classical case just in the lecture before. Here, again, it's a bit more tricky because, well, the idea is kind of similar, but the whole setting is a bit more complicated. So a convenient way of doing this is to just formally plug it into your equation, and then you impose a condition that we call local divergence conditions, and that will give you a quadratic algebra for the AI. Also, the previous algebra we saw with the exclusion was a quadratic algebra because it's bilinear in this matrix that appear. And so this will give you some algebra. Then we have to derive boundary relations for these vectors from the boundary parts, from the dissipator parts, and solve some eigenvalue problem. Then finally, you have to find a representation for this quadratic algebra. That's the program. Okay, now the matrix product ansatz, the first idea, which again was a very clever idea by Brosen, is to decompose your density matrix in this form. So remember, rho should be unitary. So you can always write as S times S dagger with some matrix S, and then you normalize by the trace of S dagger. So S, again, is some matrix of dimension 2 to the power n. Yeah?
Excuse me, I'm a bit confused. The steady state density matrix is going to be confused of eigenstates of the sub-Hamiltonian.
Not eigenstates, no.
As a superposition of the thermal or non-thermal superposition of these eigenstates.
Well, no, density matrix you do not express in terms of eigenstates of the Hamiltonian. Density matrix is something more general. A density matrix is, well, what shall I say? Formally, it's just a matrix from which you can obtain all kinds of observable, taking a trace of the matrix times observable. The eigenstates is what you need when you have what is called a pure state, with a density matrix which just factorizes into a bra and a cat. But this would then be equivalent to an isolated system without any environment. If you have an environment, you have to go beyond this factorization and take a general matrix, which is just Hermitian and positive and has a finite normalization.
Okay, so my system is not converging to a superposition of the original eigenstate.
No, it will not, no. Correct, it will not. Yeah. Yeah, good that you made this point because this is quite important. So anyway, since Hermitian, I can decompose it in this way. So again, into a matrix of this dimension. So this decomposition alone doesn't take you very far. However, somehow it's simpler to make a matrix product ansatz not directly for this rho, but for this matrix S. Now, matrix product ansatz means that you take a matrix of dimension 2, raise it to a tensor power n. This will give you a matrix of dimension 2 to the power n. But now the entries of this matrix, these are not numbers. These themselves are matrices. In other 8 matrices, of which at this point we don't say anything. They're just matrices acting in some auxiliary space. And then these vectors, they will be vectors on which these matrices act. And then the scalar product really is acting on these matrices and not on the overall tensor product of dimension 2 to the power n. So if we take this tensor power, that means that this will be a matrix of dimension 2 to the power n, but the entries themselves are products of matrices. And the matrix elements of S, they are these scalar products here. So we take this inner product with these vectors in this auxiliary space. So this will be the matrix elements of S, and this will be the matrix elements of the tensor power, nth tensor power of this 2 by 2 matrix omega. That's just the structure of the ansatz. Now, what can we say about these matrices, right? We have to make sure that this ansatz will solve our stationary Lindblad equation. And for this, well, we have to write it down, get the quadratic algebra, and show that we can actually find representations that solve this quadratic algebra. And this, fortunately, is possible for the problem that I've shown you. In order just to show the solution, let me remind you of the parameterization of the anisotropy as, oh, there is a fact 1/2 missing, sorry, q plus 1/q divided by 2. And now I introduce the so-called q symbol. So xq is just q to the power x minus q to the power minus x divided by q minus 1/q. This is just the definition. And then my matrix I just introduced, I set them equal to I times another matrix, the A1, so this would be A plus minus. The A1, which was the upper left on the diagonal, I set I times this q expression of the matrix SZ, and A2 I set minus A1. And then the local divergence condition, which we impose on these matrices, that will be solved if we assume that these matrices S plus and S minus, which are equivalent to the A's, satisfy a certain algebra, which is called the Q-deformed algebra of SL2, and which is defined in this way. So it's almost like the, and there's another typo, I apologize, should be 2 times SZ here. So the commutator of S plus and S minus, in the normal SU2, this would be just 2 times SZ. But here it's the Q number, the Q expression of 2 times SZ. And the commutator of S plus and S minus is just the usual one, as in SU2. Okay, so this will solve our equation. Now, since this is a known algebra, we can actually look up the representations, and they are given here. They're infinite dimensional. So SZ will be infinite dimensional diagonal matrix. S plus will be an infinite dimensional spin raising operator, and S minus will be an infinite dimensional spin lowering operator. And what you have inside is an arbitrary parameter P, which can be complex. Remember, we do not require these matrices to be Hermitian. They can be just anything. Now, on top of that, we have these boundary relations that we have to satisfy. And in our case, there are 2 boundary relations for each vector. And this is just the form. So we have our left boundary vector, and acting with this combination of these matrices, this has to be 0, and also this has to be equal to 0. And then there's a similar set of equations for the right boundary, where again this theta L is the twisting angle in the left, and the theta right is the twisting angle on the right, in the right boundary. Now, vectors that satisfy this equation, again, we can find, namely these are kind of generalized coherent states. So we just take the raising operator acting on 0, and take the nth power with this kind of product here. So basically, we take an exponential of S plus with the parameter phi, which would normally call a coherent state. So it has this structure. And for psi, we get something similar, which in this representation just phi to the power n. This n factorial cancels in the way how this S plus is defined. And here in the S minus, you get a binomial coefficient instead. Okay, and now we solve this boundary equation simply by setting these parameters phi and psi to relate them to the tangent of the boundary angles. So the left one we choose, for simplicity, we choose to be 0, and the right one we choose to be equal to theta. And it turns out that this parameter p has to be equal to I times I over the coupling constant, which gives you the strength of your Lindblad terms. So in this way, we obtain an explicit expression for this matrix S, from which we can compute rho. So here is rho, again, to remind you, it's S times S dagger divided by the trace. And now we can play a little bit, and we realize that also the rho itself has the form of a matrix product. Namely, it's the nth tensor power of another matrix, which is just given by this omega p, which is a 2 by 2 matrix with this matrix S plus and minus and SZ inside. And then we take a matrix product in this 2-dimensional space, but a tensor product in this auxiliary space. And this gives you a matrix P of rho, which again is 2-dimensional. And then we take the scalar product, and we get the density matrix rho. The boundary matrices are again tensor products, and then we have rho. Now, how do we compute expectation values? Given this rho, well, it's very similar to what we saw in the classical case. We define matrices B alpha, which are linear combinations of the matrix elements of pi. For instance, the B0, this would be just this object here. And then the normalization would be B0 to the power n, very similar to what we just saw, where the normalization would be D plus E to the power n and in the scalar product. The local magnetization at site K, what we have to do is, in this product of n matrices, we have to replace the B0 by a B alpha. So we have a K, B0 to the power K minus 1 times B alpha for angle alpha, for direction alpha, and then B0 to the power n minus K. For correlations, we replace two of these B0 matrices by B alpha matrices. And so on. So higher order correlation functions, you just replace at each site where you want to have some magnetization operator, you just replace the B0 by the corresponding B alpha. That's how it works. And then this object will be the trace, this will be your quantum observable, the trace of the corresponding operator times rho. That's the way how this is the magic of this product, matrix product ansatz. So a correlation function we just take to be this 2 times this 2-point expectation value minus the product of the 1-point expectations. So what we can do now is, well, we have solved this problem. Of course, it's still complicated because computing these traces, this scalar power is still a difficult problem, but at least it can be done numerically for pretty large n. And in some cases, we also have exact asymptotic results, but not too many yet. Okay, so now what comes out? Let me mostly talk about the XXX chain, namely where delta is equal to 1. So we have a fully isotropic interaction along the chain. So the Hamiltonian is just this S vector times the exchange coupling constant. So it's just equal to this. In this case, this quadratic algebra, which was this Q-deformed SL2 algebra, is just the usual SU2 algebra, which comes from the fact that you have this rotation invariance in 3-dimensional space, but since it is a quantum system, not O3, it's SU2. Okay, now since we have this rotation theory in 3-dimensional space, and if we want to twist our boundary spins, right, the only thing that counts, since we can, if we have, let's say, this twist, we can rotate in any way that we wish, right? It's all equivalent. So we just choose at the left end a polarization along the x-axis, and then in the other end, we choose a polarization in the xy plane with a twist angle theta, which can be non-zero, right? So this is just a choice of coordinate system. This is completely general. Okay, now then we compute the Lindblad, the dissipators. I've shown you basically how to do it. And now we begin computing quantities of interest. So first of all, let's look at the currents. Now, if we have a rotation invariant system, not only the Z component of the current will be conserved, but all 3 components of the magnetization currents will be conserved. You can simply see it by noticing that if you look at the derivative of the operator, the spin operator sigma n alpha, which by definition is the commutator of h times sigma alpha times factor a, you will see that this is a difference of 2 current operators. And the fact that this difference is really expressing the fact that you have a conservation law, because if you take the sum over all n, let's say on the periodic chain, this would be 0. That means all 3 will be conserved. And the local currents, if you can compute them, you will find out that they have just of this form. So they're a product of 2 neighboring spin matrices with the Levi-Civita symbol here. So in the stationary state, obviously, these currents must be constant. And I just call them capital J alpha. Now, what comes out from the matrix product ansatz is the following. These are exact expressions. Again, Z of n and theta, this is the coupling constant. And I have omitted the strength of this of the Lindblad coupling, which I don't want to talk about very much here. So the X current is the ratio of the 2 normalization factors for n minus 1 sides and n sides times 8 over gamma times the coupling strength. Then the Y current is just minus the cotangent of theta over 2 times the X current. And finally, the Z current is minus 4 times the derivative of the normalization with respect to theta for n minus 1 side divided by n sides. So that means that we can express all the currents just in terms of these normalization factors, which is the trace of this B0 to the power n. That's nice because all we need to do basically is to somehow compute this normalization factor, which is the kind of non-equilibrium partition function of your problem. Okay, let's first look at theta of twisting angle non-zero and pi. If the twisting angle is 0, the system is trivial. It will be just a very trivial factorized state with a polarization along the x-axis. So this is not very interesting. But if you take a non-zero twisting angle where we induce a current, then the normalization factor grows with system size asymptotically as 2n over theta to the power squared. Now, this is something I should say we did not really get analytically. We got it from computing these factors up to large n, about 100, and then we saw that it behaves like this. We can prove it only for small theta, but we believe it's generally true. At least as long as gamma times n is larger than 1. So if, let's say, gamma is a constant, we take n large, then we'll be satisfied. Now that means that in the projection plane, the x current will be 2 over gamma times theta squared over n squared. So it will be 1 over n squared. Whereas on the x-axis, along the current along the z-axis perpendicular to the projection plane, the current will be 2 theta over n, which is proportional to 1 over n. So now, if we now look at n times the current, we will see that this will be 0, whereas this will be constant. That means that the current in the projection plane will be subdiffusive, whereas this will be a current like in normal diffusive transport. So that's what we find here. And here just some pictures. Here you can see the x current as a function of this gamma. So it goes down like 1 over gamma, as predicted, for different n. And here you see the z current as a function of the twisting angle. So you see that really, this is again for the same set of values of n, and 50 is the green curve. So the longer we take, the more it approaches this prediction 2 theta over n. So at this is 2 times theta. So at maximum twisting angle pi, this current actually on this scale drops to 0. Well, it will be actually of order 1 over n squared, more precisely. But anyway, so you really see it's a linear function of theta if you make n very large. Okay, now let's look at the magnetization profiles. Well, let me just define the unnormalized profile. So remember, this object here is the magnetization profile. You get the magnetization at site k for component alpha just by replacing the B0 by a B alpha, and then you have to normalize, right? So this is just the unnormalized magnetization profile. Now, it turns out that this SU2 algebra for this matrices S plus minus induces a cubic algebra for this matrices B, which looks like this. So it depends on the representation that you choose. It has this representation parameter inside. Now, this is a very interesting observation because this allows us to obtain recursion relations for these objects here. Namely, in particular, for this unnormalized normalization, you get this recursion. It's recursion in the position and in system size. So it's a double recursion, right? Now, this recursion one can try to solve. We tried pretty hard. We haven't managed to get a closed form expression for it yet. However, we can, again, just plug it into a computer, solve for finite n. That's what you've seen on the previous slide. Or we can actually kind of turn this equation by just making a continuum approximation. We take n very large, we take the lattice spacing, then we rescale space so that the lattice space becomes 1 over n, and then this recursion relation actually becomes, with the normalization factor properly included, a differential equation. And this we can solve. And this differential equation is remarkably simply. It's just a harmonic equation. That means that your magnetization profiles, if you take n very large, and you introduce a rescale coordinate. So basically what it means is you take your k somewhere in the bulk, make it very large proportion to n, so that u remains a constant. Then your magnetization in alpha direction at site k becomes a function of this coordinate u. And specifically, the x component will be cosine theta u, the y component will be sine theta u, and the z component will just be 0 on in this limit, where n goes to infinity. And it does not depend on this gamma, as long as gamma is just a finite number, or gamma n is larger than 1. That's why I didn't talk too much about gamma, the coupling strength. So here you can see some results. Now what you see here, the points, this is an exact numerical solution for 40 sites, gamma equal to 4 and theta equal to pi over 2. And what I'm not sure you can actually see is that there is also a line that goes through these points, which is just the cosine and the sine respectively. So there is no visible deviation between the exact numerical result and this continuum approximation. Now, this was for theta non-zero and also not pi. If you take theta equal to pi, the driving is maximal. So you fix at one end in plus x direction, and at the opposite end you fix in minus direction. that means you have an extra symmetry. Namely, you can rotate about the x-axis and nothing will change. And then, well, the pictures change a little bit. Then the y and z currents will be exactly 0 for any system size. And the x current will be of order 1, will remain of order 1 over n squared. So basically it means that you will have a subdiffusive current also in the direction of your projection. Now you can use again the cubic algebra for the B matrix and take the scaling limit, and then you will get expressions for the profiles and also for the correlation functions. And it turns out that in this case the y and z magnetization are 0, like the currents, but the x magnetization will be a cosine pi times u. And this is some work by Brosen and Bucher and Brosen from that's very recent partly. The x correlation at 2 different points, scaled points, is the following. It's minus 1 over n times u times 1 minus u2 times pi squared times some function of u1 and u2, which is just basically the product of 2 sides here. Now, what I find remarkable about this formula, exact formula, is that what you see here is exactly the correlation function that we got for the symmetric exclusion process of this classical system. So this times that will give you the quantum correlation function. Now, let's have, before I finish, let's have a last look at the XXZ chain. So where we now take our ZZ coupling, anisotropic, different from the YY, from the coupling in the projection plane. And then, we can look again at the currents. Now, first of all, there's only one conservation law now. Only the Z component of the magnetization will be conserved. Let's forget the entropy at this point. Let's just look at the current as a function of delta. And since in this case we do not have an exact solution in general, we just did it numerically for 4 sites. So the black curve is the current, and here's delta, the interaction strength. So you see that the current is almost 0, except around a particular value of delta, where it actually is almost maximal. The maximum value is plus or minus 1. It cannot be bigger by definition. So you have a kind of funny resonance. And then we looked actually at this point, and we realized the following. And this is again exact. If we choose delta to be the cosine, the interaction strength, to be cosine of the twisting angle, plus a multiple, an integer multiple of 2 pi over n minus 1, and then we can choose any gamma, then, and this is an exact result, Jz will be sine theta, so it will be of order 1. There's no 1 over n, so it will be a ballistic current. And there's this resonance that you see here that makes it really of order 1, not order 1 over n. Your magnetization profiles, they will remain unchanged compared to what we saw before. But the current at this particular value of delta will be ballistic. Now, nevertheless, there is a change, because before theta was just some number between 0, just some twisting angle. But now we can add this value. It will not change the value of your theta, of your boundary twist. However, it will change the density profile. Namely, it will introduce extra windings. So here, if n is equal to 0, you will, this is just, and they take theta equal to 0. So just the most trivial case, take no twisting angle, but take winding number 0, well, then you just have this linear, just this constant magnetization profile. But if you take a winding number n, if you take delta to be equal to this value, well, then you get a non-zero, you get a non-trivial profile, you get a non-zero current, and you get a winding of your spins just once around the chain. And if you take n equal to 2, you'll get 2 windings and so on. So you can introduce non-zero winding numbers, even though the twist angle is always the same, just by adjusting the interaction constant appropriately. So this is clearly some quantum effect that has no classical analog as far as I know. So let me conclude. So we have a matrix product construction for the stationary Venn matrix under some assumptions of our Lindblad coupling. Of course, will not work generally, but for specific coupling constants we can do it. And if we have these local diversion conditions, we can derive a nice quadratic algebra and also boundary relations. Now, if we take the isotropic chain, the current will be suppressed in the projection chain. It will be anomalous subdiffusive transport. And the current in the z direction, perpendicular, this will be just normal current. the magnetization profiles and the correlations, however, they're kind of reminiscent in some sense of what we saw in the classical case, where we have nice general theories. If you have the XXZ case, then again, we have a current resonance, a non-zero Weinstein number, which I believe is a quantum phenomenon. I cannot imagine anything happening like this in a classical situation. Well, so these are the results, but of course there are many open problems. One is this result for XXZ. This was for the exact result was for a very specific choice of delta and boundary twists. So it would be nice to be able to know what is the most general boundary twist that we can do for the XXZ chain and still solve the problem. This has not been worked out yet. Maybe it cannot be more general. We simply don't know. Then it would be good to extend this to other quantum systems with higher spin or nearest neighbor higher spin, for instance, to see what of this remains valid. And then, of course, one would like to get a full hydrodynamic description of this phenomenon. It's not even clear there is one, but it sounds plausible because we see these analogies to classical systems where we have these very nice hydrodynamic theories. And with this, I would like to end and thank you for your interest.